Rethinking the core principles of pipe stress and flexibility analysis. Part 1: The role and importance of piping and pipelines in the industry. Introduction. Mistakes, errors and disasters. ASME B31.3 is clear on the fact how piping flexibility analysis, or stress analysis in common terminology, is tied to piping design in terms of required educational and related practical piping design experience. It does not, however, advise on the level of experience, familiarity, or understanding that piping personnel not directly involved in stress analysis, from piping designers and engineers to project engineers and project managers, should possess in relation to piping flexibility analysis or stress analysis issues. The course title should be self-explanatory, but we would also like to add clarity to some of its important aspects. It's been noticed from experience that pointing to the source of all problems is the key to understanding and solving most of the errors and mistakes that occurred in the process of pipe stress analysis applications in the design. And although there may be people who disagree, since there has been a lot of effort invested in this issue, but the most common mistakes still come because of miscommunications and misunderstandings, from both sides of the spectrum. Eliminating any arbitrary interpretations of this apparent but unspecified requirement would result, and that was the intention, in piping flexibility analysis, commonly known as stress analysis, becoming recognized as an integral part of a measurable engineering effort on a project, and not just a quality control tool. Thus opening the door to possibility for implementation of proactive engineering methodology, and benefiting projects not only with increase in profitability, but also in overall safety and reliability of designs. In order to achieve this, the course will be rethinking the core principles of pipe stress and flexibility analysis, aiming at contending the challenges of how to spot the difference and disentangle a well-done pipe stress job from an incomplete, inadequate or improperly done job. Then, how to use available knowledge to its maximum potential, in the context of the proverb, which is saying, that more important than how much you know, is what you are capable of producing, with what you know. And, how to take away the pipe stress job from being a routine job and just a quality control tool, and place it where it belongs, in a domain of creative thinking processes and an integral function of a measurable engineering effort on a project. It is well known that piping and pipelines play a significant role in the industry, but it would be good if we could somehow also quantify this. There are a number of sources elaborating on the topic. So let's see what one of them has to say. Around 25 to 35% of all material expenditure is spent on piping on a typical process plant. Also 30 to 40% of all installation works. And finally, what is important for us to know in the seminar, 42 to 48% of all engineering effort is spent on piping. So we see that almost 50% of all engineering time is spent on piping. Part 2: Causes of catastrophic incidents. Mistakes, errors and disasters. Introduction to failure analysis. The tank lifted off and was found on top of the unit. This was an amazing event, having in mind the knowledge that pneumatic testing always involves the hazard of a potential for sudden release of energy stored in compressed gas, and if we also assume that the following procedure, which specifies the basic requirements of pneumatic testing, should have been followed, as per ASME B31.3 and ASME Section 8 Division 1. In essence, the pressure should have been gradually increased until a gauge pressure that is the lesser of 1/2 the test pressure, or 170 kilopascals, 25 pounds per square inch, is attained. At that time, a preliminary check should have been made, including examination of joints in accordance with B31.3 requirements. Thereafter, the pressure should have been gradually increased in steps until the test pressure is reached, holding the pressure at each step long enough to equalize piping strains. The pressure should have been then reduced to the inspection pressure before examining for leakage in accordance with B31.3 and ASME Section 8. Here can be seen from another angle the extent of damage. Note the unadulterated workout of energy that was stored for the test. Difficulties with pneumatic testing. Pneumatic tests are potentially more dangerous than hydrostatic tests because of the higher level of potential energy stored with compressed gas. Care must be exercised to minimize the chance of brittle failure during testing by initially assuring the system is suitable for pneumatic testing. It should be always kept in mind, damages made by failures in pneumatic testing can be huge as shown on these photographs. Therefore, pneumatic testing needs special attention and more rigorous safety precautions. Using a pneumatic test instead of hydrostatic requires approval from proper authority or body. Pneumatic tests could be performed only when at least one of the following conditions exists. A. When the systems are designed in such a way that they cannot be filled with water. B. When the systems are such that they are to be used in services where remaining traces of the testing medium cannot be tolerated. A typical flare system consists of PSV outlet pipes, sub-header connected to main flare header connected to knockout drum, outlet of flare knockout drum to flare stack. A knockout drum to remove and store condensable and entrained liquids. A single or multiple burner units and a flare stack. Piping shall be evaluated for flexibility and expansion loops shall be provided wherever necessary. Expansion joints shall be avoided. Flare piping loops are planned in horizontal plane, 2D bends, in order to ensure pipe slope for free draining requirement. From this angle, it looks like that due to large thermal growth of the horizontal section, before the expansion loop, pipe movement simply exceeded the available sliding space. This is very important and could be perhaps what caused the collapse at linea de flare. The guide supports mounted on both sides of the expansion loop, G1 and G2, as shown, play an important role in the functionality of the loop. The elbows should slip through the axis of the main line, instead of slipping laterally. The thermal expansion loops can be symmetrical or asymmetrical, in terms of their position in between the anchors or fixed supports. Also, the important question that may have not been considered is, when does the expansion loop become too large, so that the line needs multiple expansion loops instead of one? More than one loop may be essential when the forces required to bend the loop are too great and the anchors cannot be economically reinforced. Anchor forces become too unbalanced and steel cannot be economically braced. More than one loop may be required also when the displacement at support points cannot physically be tolerated by the bearing surface of the support structure. In other words, when bearing surface has been the limiting factor which has to govern failure to meet the mentioned criterias, and considering the particular physical concepts may cause failures. Perhaps, the displacements became too large for supporting structure to hold up, the support type was not properly selected for guiding purposes, they should have had hold down possibility also, and the forces exceeded the load carrying capacity and lateral direction. Therefore, the line has collapsed by slipping laterally. It would be nice and neat if there were only one cause per failure, because correcting the problem would be then easy. However, in reality, there are multiple causes to every equipment failure. Unfortunately, there are many people who believe that there is only one cause for a failure. Some roots of failure can be traced back to 30%, manufacturing errors, 26%, design errors, 23%, maintenance errors, 18%, material selection, 3%, operation. Part 3, Major Contributors to Accidents Due to Project-Related Issues. Introduction to Failure Analysis, Possible Causes of Accidents, Type Stress Analysis. Causes of failure can be found in the roots of a physical realm. Physical roots of the problem is the mechanism that causes the part, or the system to fail. Failure analysis must start with accurately determining the physical roots, because without that knowledge actual human and latent roots cannot be detected and corrected. The human roots are those human errors that result in mechanisms which cause physical failures. The major human errors are divided into 6 categories as follows. 1. Design. There are 2 types of design errors, those of omission and those of commission. An omission error is one in which the engineer or designer fails to notice a design flaw that results in a premature failure, such as a stress concentration or an improper material selection. B. A commission error is the one in which the decision is made to use otherwise acceptable design, under conditions that led to failure. 2. Manufacturing. A manufacturing error occurs when a machine that was properly specified and designed is improperly manufactured. Now that the event has been clarified, root cause analysis logic tree follows as shown. If the root cause analysis is not required, the report is filed and the originator notified. However, if the root cause analysis is required, data should be gathered to clarify the problem, or the event. And if this is an equipment or system problem, continue with following the root cause failure analysis guidelines. If not, the design is first to be checked through performing a design review. The first question is: if the problem is solvable based on design review, in other words if it is a design-related issue, and if the answer is yes, shortcut is in the development of corrective actions. On the other hand, if the problem cannot be solved through design review, proceed with application evaluations and question if the actual parameters are consistent with the design. The yes answer would lead again to a deeper analysis and RCFA sequence, and now would instigate another question, which is: can a problem be solved based on application evaluation? No would mean again going to RCFA sequence, but yes would be a more desirable and a road towards developing corrective actions and performing a cost-benefit analysis. Out of which a question would arise: is cost-effective solution possible? And if it is, recommendations would be submitted for approval, based on which would proceed with the implementation of corrective actions. In the event of recommendations not being approved, the process would return to the reworking of the corrective actions. Also, if the solutions provided would not be cost-effective, the whole process would be filed and a search for cost-effective solution continued. As we have seen, piping department has to interrelate with other departments or parts of the project. However, within piping department itself, two major groups are operating. One is piping engineering group, and the other, plant design and layout group. Piping engineering, as shown here, besides with piping design and layout group with which the link is the closest, interfaces also with other groups and departments outside of the piping department. In some instances, when piping design and layout is part of the piping engineering group, in organizational sense, we can define the following piping engineering subfields categorization: piping materials, piping design and layout, and piping flexibility analysis. All should be cognizant of the Flixborough, England, disaster in 1974. This disaster was caused by a poorly qualified design team that installed temporary piping. Their lack of understanding claimed the lives of 28 people and cost $100 billion in material damage. The subsequent investigation revealed the following: even though a significant crack, 6 feet long, was found in Reactor 5, the urgency to resume production distracted staff from critical consideration of their plans that could have identified the hazards involved. And they failed to fully assess the significance of what they were doing. So the decision was made to restart the process without inspecting the other reactors to determine if similar cracks existed. While calculations were made to confirm that the 20-inch pipe could withstand the normal working pressure, no consideration was given to the bending moments or hydraulic thrusts that would be imposed on the assembly. There was no reference made to vendor manuals for the expansion bellows, nor to relevant British standards. One only needs to review these photos to realize the consequences and to link that with the importance of piping flexibility analysis. The details of the accident can be found on the internet. Part 4, Addressing the Root Cause of Piping Design Errors. Pipe Stress Analysis from Global Project Perspective. Reactive or proactive methodologies. Choosing the right methodology for flexibility and stress analysis of piping systems is essential. The way flexibility analysis is used could directly influence overall project results. So the best way to explain its importance would be with describing flexibility analysis through reactive and proactive design methodologies. In working with the reactive methodology, stress engineer is actually placed in the position of design verifier. Therefore, he will be verifying the designs that could have been produced, either by inexperienced designer, or by experienced designer. The design that will be produced by inexperienced piping designer usually comes for stress verification with insufficient flexibility. On the other hand, design that is produced by an experienced piping designer would come for stress verification and will be too flexible. In both cases, stress engineer would be requesting layout rework, the difference being that the inexperienced designer would be given a request to produce new layout concept with more flexibility, whereas the experienced designer would be usually required to come back with a modified supporting configuration while keeping the same layout. In the end, either side will affect project results in a negative way, with inexperienced designer affecting the project through a slow process and long schedule, while experienced designer will affect the project through wasting space and the excessive use of materials. Here we see a flow chart of activities on pipe stress analysis, but from a project engineering perspective, and we are not going to go deep into it because this is a topic for itself and will be worked on in detail in a separate course of study. Therefore, we will just discuss the vital issues, and which are the decision boxes representing some turning points, which are of significance for proper organization of flow of information. After the start of analysis based on critical line list, as well as other priority lists, the most important is to explain the decision crossroads in the typical flow of activities on a typical project. There are 5 decision crossroads. The first one is the system ready for stress analysis. In a project sense, means asking if the adequate important holds have been removed in communication between design and stress, so that stress analysis can go ahead, based on assumptions that will not impede on validity of the conclusions from results. Second, have the issues been identified, meaning, has the stress analysis identified any issues? Third, are there any comments, meaning if the reviewers of the interim report came back with comments? Fourth, is the question of so-called critical holds been removed? The question here is if the analysis could be actually finalized, and the fifth logical decision crossroad is at the question, can the stress analysis report be issued with non-critical holds remaining, only upon which, final reports could be issued for use? It is important to emphasize that in this system, there are actually 2 once-through coolers involved, low-pressure OTC and high-pressure OTC. The hot air is in fact the exhaust gas coming out of the compressor of a gas turbine. It is cooled down with the help of water in the once-through cooler. The cooling feed water is actually taken from the economizer of a HRSG, heat recovery steam generation unit. It flows through the OTC, once-through cooler, cooling down the hot air, and is evaporated when leaving the cooler. This vapor is then used in a steam turbine. The cooled air flowing out of the once-through coolers will hence be used to cool down the blades of the turbine, and it is therefore re-injected to the turbine. As the cooling of the blades on the turbine is very crucial, a too cold gas can definitely damage them, and a too hot gas can fail to cool them sufficiently. The outlet temperature of the air from the once-through cooler is very important, and is the variable that will need to be controlled. Benefits of computational analysis of stresses in pipes and piping components can be seen not only in design analysis but also in forensic investigations of failures. Actually, due to an incident on the previously analyzed and properly designed gas turbine air cooling system, where a weld seam at steam outlet failed, producing considerable damage, an investigation into the incident was carried out. The aim was to find possible design reasons for failure, and generate necessary corrective design actions which will rectify the situation, and produce a new solution, ensuring future integrity of this type of piping designs. 3 parties were involved in the original design which affected the location of failure: Gas Turbine Air System Design Group, OTC vendor, and Plant Design Group, and the failure occurred just below the interface line between plant and OTC vendor. So theoretically the failure point was in the jurisdiction of OTC vendor, but he has therefore as a safeguard, defined the allowable load limits at the interface point, and plant has made sure with their analysis, to fulfill these requirements. For the same reason, plant have also used appropriate displacement values from the gas turbine air cooling system analysis, which has been provided to them by Gas Turbine Air System Design Group. It was found that regardless of the fact that everyone did their part properly, there was little cooperation in the reactive design methodology, which everyone has followed, and that they all missed out on a very important fact. Which is, that dissimilar metal weld, when cannot be avoided in joining piping systems, create a somewhat peculiar situation, where design for various reasons may result in producing joints weaker than expected, and create a situation where failure due to fatigue may occur much sooner than expected. Based on everything revealed here, and as a first step towards new rectified solution, a practical most advantageous spot for possible relocation of the dissimilar metal welded joint was selected as shown. Firstly, it is obvious that the location of dissimilar metal weld should have been discussed at the very early stages of the project, and finally, that this could have only been possible if the proactive design methodology was in place, instead of the reactive methodology, and this exactly has been identified as the root cause, or the main reason which led to catastrophic failure. Part 5. Stress and Flexibility Analysis of Piping Systems. Piping systems from pipe stress analyst's point of view. To answer the question, what is a pipe stress engineer? In terms of essential educational requirements and experience, he or she must hold in practice bachelor or master's degree in engineering. As per ASME B 31.3 Piping Code Chapter 2, A, completion of an engineering degree, requiring 4 or more years of full-time study, plus a minimum of 5 years experience in the design of related pressure piping. According to ASME B 31.3, a designer, pipe stress engineer, with a lower formal education than bachelor or master degree, needs 10 to 15 years of practice and supervision in order to be responsible for the design, pipe stress analysis. Pipe stress engineer must also have an understanding of codes, such as ASME codes, federal, state and local regulations, as well as industry practices. Pipe stress engineer will be working with piping stress analysis software on a daily basis. Persistently follow new developments in codes and participate in programs for continuous education of engineers. So the role of pipe stress engineer is intricate and demanding, but in many aspects also highly rewarding. First, we will try to provide in simple words explanation to two major concepts, such as, what is stress? It is defined as the applied load per unit cross-section of the specimen. The common units are PSI, pound per square inch, kPa, kilopascal, MPa, megapascal or Newton per square millimeter. And what is flexibility? The best way to describe it is when talking of rigid or flexible structures. It is that they could be specified as attributes of a structure, defining its ability to change shape under applied load. Rigidity would be the property of a structure that it does not bend or flex under an applied force. And the opposite of rigidity would be flexibility. The major stress categories are primary stresses. These are developed by the imposed loading and are necessary to satisfy the equilibrium between external and internal forces and moments of the piping system. Primary stresses are not self-limiting. Most frequent primary stress is the one produced by weight, and they are non-self-limiting. Because once plastic deformation begins, it continues unabated until force equilibrium is achieved, or until failure of the cross-section occurs, and failure can be prevented only by the removal of loading. Thus, in conclusion, primary stresses are non-self-limiting, since local yielding does not reduce them as they increase. Secondary stresses. They are developed by the continuous structural displacements. These displacements can be caused either by thermal expansion, or by outwardly imposed restraint and anchor point movements. Secondary stresses are self-limiting. Self-limiting stresses are, for example, stresses caused by thermal strain. A heated pipe will expand for some percentage of its original length, according to its thermal expansion coefficient, and if unrestrained will not show any stress in material. If the material, however, were to be constrained, it would show the stress being created, and would continue increasing until eventually reaching a yield point. From there on, where material starts yielding, stress relaxation begins, meaning that local yielding can relieve the conditions that cause the stress, and we say that this type of stress is thus self-limiting, or that strain helps with relieving the stress. Peak stresses. Unlike loading condition of secondary stress which cause distortion, Peak stresses cause no significant distortion. Peak stresses are the highest stresses in the region under consideration, and are responsible for causing fatigue failure. There are various industry guidelines for handling highly localized stress. It is worth noticing, though, that in some cases high peak stresses in small local regions cause no problem, because of redistribution of stress due to plasticity. According to Vertex, a renowned forensic firm, a common piping failure is rupture of the piping wall due to excessive stress. This piping failure mode is common in, for example, freeze failures and results in a characteristic fish mouth appearance, named for the split and deformation of the pipe wall which resembles a fish mouth, as can be seen from the photos. It is a primary stress rupture, where the surge in pressure results in increased stress in the pipe wall, exceeding the strength of the piping material, and ultimately leading to failure. In pipes, fluid pressure exerts a force in all directions. And in pipe ruptures, the type of stress that is most critical is known as hoop stress. Hoop stress occurs from the resultant forces acting in the normal direction, or tangentially to the radius of the pipe, as shown in the diagrams. Thermal expansion of piping systems would be best described in analogy with railroads design, on the following diagram. If the rails are tied together without the possibility to expand, the resultant would be as shown in option A, which is lack of flexibility leading to distortion. However, in option B, we can see that there is provided just enough spacing to accommodate thermal expansion, which also allows for proper service. In option C, too much space was left for thermal expansion, so the service would be poor. The totally rigid system, on the other hand, would be quite a good answer, but the design is heavy and costly, so it is not a viable solution. The aim of piping flexibility and stress analysis would be to find the way to option B, thus satisfying proper service with sufficient system flexibility. Part 6. Generally about piping and pipelines. Typical analysis mistakes. Along with the development of various plants that use interconnecting piping and pipelines in order to form the whole, increasingly complex demands are imposed on their design. These need to fulfill the preset technological requirements as well as additional need for reliability, with minimal capital expenditure and operating costs, optimum level of constructability, and to meet the criteria of safe working conditions for operators. In order to accomplish all of the above in piping and pipeline design, it has become necessary to resort to using specialized computer applications. Piping and pipelines are used in energy transfer, transportation of various materials and process plants applications. In pipeline and piping design, special consideration of the following needs to be taken in material selection: chemical characteristics of the fluid, fluid temperature, fluid pressure. Generally, there are three basic types of piping and pipelines: process, energy, and transportation. Piping and pipelines can be mounted either above or underground. Above-ground piping can be low-mounted or high-mounted. Underground piping and pipelines can be channel-driven pipelines, or buried and/or pre-insulated. Examples of such piping and pipelines can be found in power plants, cogeneration plants, refineries and petrochemicals, oil and gas upstream and downstream processing, as well as in other industrial and process plants. They could be also pre-stressed, for example cold cut, etc., or not. Here is a view of another district heating substation, and inside, low-mounted piping systems that are connected to plate heat exchanger. A plate heat exchange provides efficient heat transfer in compact size. It allows more space for installation of piping, with more flexibility, which is essential for this type of installations, because plate heat exchangers' nozzle allowable loads are by default, due to its construction, quite low, thus always producing a problem in piping design. However, if we decide to count with the benefits of compactness, we should not forget on the other side also the need for provision of excessive piping flexibility. Hence, unless the feasibility study is conducted prior to deciding to go via the plate heat exchangers route, the rushed, overall conclusion about benefits that was assumed above might be overrated, and should not be generalized. Another pipeline photographed in winter condition. Note the formation of ice. Snow and ice are the possible external loading scenarios on the system, which must be taken into account during design. Actually, because of large fluctuations in temperature between the summer and winter months, in regions with harsh climates, thermal expansion and contraction is a parameter which should be carefully considered in pipe stress analysis. Pipes should be carefully anchored to prevent excessive thermal load which may cause the pipe to buckle. And important to notice is also the following. When the temperature is lowered, there is a transition of material characteristic from ductile to brittle, and brittle failures could be catastrophic and without warning. In other words, it is vital to remember that when piping materials becomes exposed to cold, they lose their ductility and exhibit brittle behavior. Therefore, it is important to utilize tough materials for all pressure retaining components under low temperature. Piping and pipeline systems are composed of elements that are essential for their technological process function. For example, isolation valves, regulating valves, control valves, check valves, steam traps, strainers, pressure safety valves, jacketed pipe, etc. Elements that are forming the structural core of the piping and pipeline system, which are not responsible for the technological function it performs. For example, bends, tees, reducers, flanges, expansion joints, etc. And elements for maintaining the structural integrity by controlling stress and design life expectancy of the piping and pipeline. For example, supporting and restraining systems. Example of special piping systems where the piping can also perform an energy transfer role or other process functions. Can be used in various industrial processes where it is necessary that the transport of fluid is carried out at the predefined temperature. Optionally, vacuum jacketing is also used as an insulator for cryogenic fluids. Transported fluid is heated or cooled with another fluid, flowing around the inner pipe and through a heat transfer process maintaining the technologically predefined temperature. Heating medium flowing through the cavity between the core pipe and the jacket can be steam, hot water, hot oil, or some other heating medium. Bearing in mind that in this case, outside and inside pipes, which form the whole, have different operating temperatures, it is obvious that different thermal expansion problems can occur. Therefore, it is necessary to solve these complicated challenges of thermal expansion compensation, while maintaining the piping stresses within the allowable limits. Jacketed lines can be mounted with or without elements for thermal expansion compensation. And supporting problems are similar to those of single piping non-jacketed systems. Part 7. Some common mistakes in performing stress and flexibility. Typical analysis mistakes, continued. Piping elements which are forming the structural core of the system consist of straight section elements, or beam elements, represented in pipe. In fact, they are beam elements with a circular cross-section. Then we have elements that are used for changing direction of the pipe system route, represented in so-called pipe fittings, like elbows for example of different sizes and radiuses, 90-degree or 45 etc., and there are elements which are used for reducing from one pipe size to another, since within the same pipe system route, we could have pipes of different sizes. And finally, there are elements used for branching the route, like equal tees or reducing tees. So the basic general pipe route is assembled out of these elements to form the structural core of the piping system. Each of these element types are covered with different standards which are regulating their use. For example, B3610M covers dimensions of welded and seamless wrought steel pipe for high or low temperatures and pressures. Or the B169, that is covering wrought butt weld fittings, for example elbows, tees and reducers. With flexible supports, movement of the pipe is not restrained, but rather controlled. Flexible supports are designed around a flexible device, spring, which enables the pipe to move while still providing support to the piping. In simplest terms, the advantage being that if designed properly, the pipe unrestrained in movement will exhibit much lower stress than a fully restrained. Flexible supports have been developed into two major categories. The most common is the design with a variable effort, and equally important but more complex, with constant effort supporting option. Variable effort, meaning that the reaction force from this support will vary with the displacement, due to the spring being compressed more or less with pipe movement. And constant effort, meaning that the reaction force from the support will not vary with displacement, and will be constant throughout the range of movements. Both of these options will have two possibilities, for either supporting from underneath the pipe or hanging it from above. Also, both of these options have their dedicated applications, and the selection of which will be based on stress analysis requirements. As it was mentioned earlier, if the stresses are within the allowable limits, that doesn't mean the system is good. It is also important to satisfy other requirements. Not taking care about the three key design constraints could be a mistake. Important to remember is that as a minimum the following three constraints need to be satisfied: stresses, movements of the pipe, displacements, load on terminals of equipment, loads. Until all of these criteria have been satisfied, the analysis has not passed and is prone to be classified as failed. And this is also indicated by the fact that the solution point falls outside of the solution triangle. If the solution point is outside of the triangle straight away, it means that the overall solution is in the failed mode. But to find out which criteria has not been satisfied, we need to look at each individually. For example, if we have a look at the solution point number 2, displacements criteria is yes, load criteria also yes, but stress criteria is no. So the overall status is not good, or the system has failed the analysis. Here we see a spring travel selection table, and we'll explain briefly the concept behind the process of selection. As highlighted, for type 254218, load range between 3.33 kN and 10 kN, and working travel of 0 to 100 mm, and a spring rate of 66.6 Newton per millimeter, is acceptable for the required spring working travel of 15 mm, in the down direction and with spring compression. The initial load, so-called cold or installation load, is set on the spring to be 6 kN. In other words, after removing spring locks when the pipe is already sitting on the spring which has been factory precompressed, will release a reaction force on the pipe of 6 kN. This load will, according to stress analysis, keep the forces on the piping system in equilibrium, and the spring will be in its theoretical installed position. When the pipe is in operating situation, it will move down according to the analysis, for 15 mm, and the spring will be further compressed, to 7 kN. On the spring travel scale, this will be at the travel position of the spring on 55 mm from zero. We see on the working travel range that the selected spring will have another 45 mm of travel, which is actually a safety margin, before it reaches 100 mm of travel, and bottoming out. So the total travel before bottoming out from installed position will be 60 mm. The pipe stress analyst should ensure that in all operating regimes, pipe travel with this spring will never exceed this distance. Bellows expansion joints will give many years of satisfactory service when they are properly designed and manufactured for specified piping system conditions. The problem here lies in the fact that here involved are two engineering areas of expertise: piping flexibility and stress analysis on one side, and expansion joint design and construction on the other. Moreover, although there are no doubt they are distinctively different, they have also been presumed as almost totally separate engineering disciplines, although both have been addressing the same code in their work, namely B31.3. So, we have the situation where knowledge related to the design and construction of expansion joints sits with expansion joints manufacturing companies, which are totally separate and often remote entities in the design process, which makes it even more difficult to combine their efforts. Securing this, however, which is explained how in additional course titled, Satisfying Flexibility and Piping Stress Requirements, with the implementation of metal expansion joints, the rewards can be significant and the created final product would outweigh all shortcomings normally associated with expansion joints, ensuring the required reliability is achieved for the projected design life. Part 8. Highlighting essentials for proper stress and flexibility analysis. How to properly analyze. Selection procedure for determining the scope of pipe stress analysis on a project consists of several stages. It is a phase of great significance, and is equally important as choosing the right methodology, because of its direct effects on project outcomes. The ultimate requirement of this procedure is informing a stress analysis register or list of critical systems for analysis, which is based on the following step-by-step approach. The selection of lines is starting from the use of following approved documents. Line list, with process conditions like pressures and temperatures, P&IDs, criticality selection criteria. Since this is obviously closely linked with commercial aspects of the project, every company has developed this through their own experiences and built it into their standard work practices, but also clients have their own. So before start, this is always a matter of negotiations. We have shown here as an example, 2 charts for initial criteria for flexibility analysis of piping, prepared for use on a project. Table 5.1 is for carbon steel piping, and 5.2 for stainless. Basically, categorization of requirements for pipe stress analysis is based on pipe sizes and design temperatures. This will determine initial level of stress analysis requirements. In the charts, the following selection categorization is prescribed: I, M, and C. The previously said could be visualized for better understanding on the following flow chart, and with it we will finish our further discussion on it. However, more on this important topic can be found in a separate course of study, Fit for Purpose Procedure for Creating and Managing Pipe Stress Analysis and Piping Design Work. From the line list and the criteria for flexibility analysis that is based on flexibility analysis working procedure, we go into creating a critical line list. From there, we have the basis for grouping the lines into coherent systems suitable for analysis, forming a stress analysis register and producing a particular stress analysis deliverable list, and creating stress sketches. With the criteria for flexibility analysis based on stress sketches, 3D models and operational and visual evaluation, the assessment can be further optimized. All in order to produce a final list of critical systems for pipe stress analysis with the official stress analysis register index. Only now, an estimate for the properly envisaged and optimized scope of stress analysis work can proceed, and for which we would gain client approval prior to commencing with execution. We will get now into the details of some essentials for proper analysis. Here's not presented all that is required, but it is a vivid sample that will give the basic idea of what we should think about, and what must be included in the modeling of piping systems, to allow for proper analysis. It involves a somewhat unique modeling technique that is usually associated with Caesar 2 stress analysis software, but perhaps to some other software as well. It is a specific concept in creating models, with weightless rigid elements and connecting nodes, C-nodes. C-nodes and rigid weightless elements are the key ingredient of the ability to simulate almost any kind of situation that we can expect to come across in modeling piping systems in preparation for analysis. Connecting nodes, C-nodes, can be used to tie one node of the piping system to any other node. This tying can be associated with nodal degrees of freedom and optional defined stiffnesses. So with this technique, also any type of tie-ins between 2 nodes can be defined, and this allows for simulating in the model anything that the stress analyst would find necessary. Combine this with possibility to use rigid or flexible, weightless, or not elements for the beams to form the structure, and the combinations of what can be modeled are endless. With this technique, we will model pressure vessels to allow for their thermal growth. Then we will model equipment connections to allow for vessel connection flexibilities, accurate modeling of existing supports, components of the structure of elastic supports, secondary steel structure, multiple temperature load cases, expansion joints, and cold springs. We will focus here just on modeling techniques in pipe stress analysis, available for expansion joints, and on what is required for proper analysis. In general, Expansion joints may be added to a piping system in order to increase its flexibility when there is insufficient room for an expansion loop, and it should be noted that the use of expansion joints is usually a last resort solution, since expansion joints can have a higher requirement for maintenance. In modeling expansion joints bellows elements, they can be with zero or non-zero length, and we are going to focus just on a non-zero option, on a chosen example of a universal tied expansion joint, as will be shown here. It is important to note also that the modeling can be done in a simple form, or in a complex form. In a simple form, from node 1115 to node 1120, defined as a bellows element, with its flexibility characteristics and an effective diameter, required for the calculation of pressure thrust force. Also, from node 1115 to 1119, where 1119 is a C node, a rigid weightless element is defined that is tied with node 1120, so that Y direction and Z direction translational movement is allowed, as well as torsional rotation, while all other movement between the node and a C node has been fully restrained. Simple models should only be used where the tie bars are either guaranteed to be carrying tension, or have nuts on either side of the flange so they could also carry compression if needed. Complex models of expansion joints are much more difficult to build than simple models, but has multiple benefits, primarily as they paint a realistic picture, which is very useful when dealing with expansion joints manufacturer and performing techno-economical optimizations. In complex model, tie bars are modeled to extend as weightless rigid elements at ambient temperature, and nodes and C nodes are tied together like pin joints, as they actually are in reality. Bellows element and pipe spool element can then be at pipe operating temperature. In summary, the complex expansion joint model involves defining as accurately as possible all tie rods and connections between tie rods and end plates, while bellows elements are finite length. Complex models are used whenever a failure is being investigated. They are normally used when the pipe diameter and number of convolutions become large. Also should be emphasized that complex models give good values for the load distribution in the tie bars. And finally, they are used when nuts are only on the outside of the flange, allowing tie bars only to carry tension. We have already spoken about key design constraints and what does it mean in terms of having a passed or failed solution, as can be seen here. One of the most important aspects of design analysis is checking its validity, or doing the sensitivity studies to gain the right level of confidence in our analysis results, or to improve their values. They should be part of the analysis process because of their importance, however this is often neglected, and not much commitment and instructions have been seen in the industry on how to do it, and whether the analysts are actually obliged to it or not. So it is downgraded to individual interpretation. However, we believe that it shouldn't be left only to that. If we focus our attention on the solutions that are in the past region, one important but often neglected aspect of the design solution is where does the solution fall in the diagram? And based on that, what is the confidence we can have in it? To answer that, by doing sensitivity studies checking, we can actually define the circles of confidence. As can be seen, circle of confidence for solution point number 1 is much bigger than for solution point number 2. Therefore we would conclude that the solution number 1 is the one that we can trust more than solution number 2, or we can make further studies on solution point number 2, to find out, why are its results so sensitive. The other aspect of sensitivity studies are the speed at which circles of confidence are increasing or decreasing with the change in model inputs. All of this drives us towards conclusion that the design analysis work is actually not completed until the sensitivity studies are done. Rethinking the core principles of pipe stress and flexibility analysis. Part 9 to 12. Pipe stress analysis, case studies. Example number 1, gas turbine blow-off system. Question number 1. How to do proper analysis although not all information is available. Question number 2. How to ensure with analysis the integrity of the design. Creating the design input data. An analysis based on the available input. Example number 2. Analysis of unwanted deformation of hot air pipe from main gas turbine bearing. Question number 1. Why did the deformation happen? And question number 2. How to defend the analysis and design. Checking the existing calculation. Adding the model of steelwork to the piping model. Simulation of clamping force effect. Example number 3, crude oil tank 24-inch nozzle. Evaluation of loads produced by piping, and design requirements in relation to local stress analysis. Question number 1, can we connect the piping safely to the tank, in its, as is piping configuration? And question number 2, can we modify the attached piping as proposed and then connect safely to the tank? Nozzle flexibilities, stress, analysis cases. Stress analysis, overview summary. Example number 4. Tank number 1. 16-inch vent nozzle N1, loads evaluation produced by vent piping, and design requirements in relation to local stress analysis. Question number 1, can we connect the piping safely so no additional load should be applied on vent nozzle? Existing and new vent line design. Pipe stress analysis of new vent line. Stress analysis evaluation. Range of operability analysis. End of part 1 to 12. Thank you for watching.